In this video, what we're going to do is talk a little bit about magnetic interactions. So you probably have some experience with this, with either refrigerator magnets or toy magnets, and even maybe in courses that you've taken in high school. So the idea is that magnets have these two poles, a north and south pole. So any sort of bar magnet will represent like this with a north pole and a south pole. And the interactions between the different poles give rise to sort of different pushes and pulls, different forces. So if we have two poles that are both north pole ends, we find that they push each other apart. Whereas if we have two poles that are oppositely signed, or one north pole, one south pole, they pull together, right? This might remind you a lot of sort of the interactions that you see with charges, right? Where the unlike charges attract and the like charges repel. So similarly, the unlike poles attract and the like poles repel. The difference here is that no matter where we look, everywhere in space, we cannot find lone north poles or lone south poles. So even though that I've drawn the sort of ends of the poles, the ends of the magnets here, there's still these ends way over here that have the sort of oppositeness of the pole that is on the left or right end. So these things always come in pairs. You always have a north pole and a south pole. Even if you cut the magnet up into a bunch of different pieces, you always end up with a north pole and a south pole. So this idea that there is some sort of magnetic, we'll call it a monopole, is what it's referred to, is something that people are actively looking for, and there are theories that include it, but we don't see it everywhere we go. Now, these kinds of magnetic interactions are mediated by something that we will call the magnetic field. And the magnetic field is what we're going to explore and the sources that produce it over the next couple of lectures. That magnetic field, we often use the symbol B to represent. And that's because the idea behind magnetism and sort of what gave rise to it was already described with an M and a vector. But the idea here is that this guy is what we're going to keep track of. Now, the magnetic field itself has units. It has some new units that we're going to introduce. So the magnetic field has units of Tesla. So, and a Tesla turns out to be a very large amount of magnetic field. You don't want to be around a 1 Tesla magnet. That would not be good if you were wearing anything that was magnetic at all. It would not be good if you had some sort of internal medical device. It could really disrupt those things. And to give you a sense of how big the magnetic field associated with 1 Tesla is, the Earth's magnetic field, which is a relatively present magnetic field, it's the thing that compasses are used to align and so forth. The Earth's magnetic field, sort of everywhere you look, is of order 10 to the minus 5 Tesla. So it's 5 orders of magnitude less than sort of a 1 Tesla magnet. So magnetic fields are relatively weak unless they're in very exotic situations like stars and black holes and things like that, or unless you construct them with very exotic materials. So this is just to give us a sense of what these magnetic interactions are and what we're going to do with them. And in the next videos, we're going to talk a little bit about their sources and how we actually produce them.